We are going to discuss resistance and resistivity. This is chapter 11 of your Cambridge A-level course book. The learning outcomes of this chapter are: you should be able to state Ohm's law, sketch and explain IV characteristics for various components, sketch the temperature characteristic for an NTC thermistor. NTC stands for negative temperature coefficient thermistor. We also have PTC thermistors, that is positive temperature coefficient thermistors. Now for your O-level class, so far you have got questions involving NTC thermistors, where the resistance increases with increasing temperature. Resistance decreases with increasing temperature, or resistance increases with decreasing temperature, or we can say resistance decreases with increasing temperature. Okay, so when one quantity increases, the other quantity decreases, or when one quantity decreases, the other quantity increases. That is NTC, negative temperature coefficient thermistor. We also have PTC thermistors. In a PTC thermistor, when the temperature increases, the resistance increases, and when the temperature decreases, the resistance decreases. Okay, and the last point here is solve problems involving resistivity of a metal. Okay, we will see this equation, R equals rho L over A. That is the only equation you will learn that has resistivity. Okay, it's a very important equation. You have to be able to use it. In past papers, I have seen questions again and again where they check this equation, where you have calculations involving this equation. Okay, so we have Ohm's law, sketch and explain IV characteristics for various components. Again, we will see graphs for that. Now once you learn Ohm's law, that is the equation we have for Ohm's law, V equals IR. Okay, and you have to plot graphs. So the gradient will be, if it's a V versus I graph, from the equation V equals IR, the gradient is the resistance. So we will go into the details. Okay, so this is for you to have an idea of what we will cover in this chapter. Okay, so resistance is one thing, resistivity is another thing. Resistivity is depending on the material. So for different materials you have different resistivities. Okay, so let's start with Ohm's law. By the way, these things also you can read for additional information. The IV characteristic for a metallic conductor. Okay, so for a metallic conductor, we have an IV characteristic. Okay, so there is an equation for this. Okay, so this is the equation. All right, so we have V equals IR, and R is equal to V over I. Now if the resistance doesn't change, for example, if it's a metallic conductor, the resistance hardly changes with changing temperature. Okay, so but actually when the temperature changes, the resistance changes, but there isn't a big temperature change in a metallic conductor, for example like a copper wire. So we can say the R is constant. Okay, now if you plot a graph of V versus I, like here they have switched the axis. This is a I versus V graph. So the gradient of this graph will be 1 over R. If you plot a graph of V versus I, the gradient will be R. But here the axes are switched. So the gradient of this line is 1 over R. Okay, so this is what they are doing. Now we will go into the details of this afterwards. So we can rearrange the equation and show you how it is 1 over R and how it is R when it comes to the gradient, depending on the axes that are selected for I and V. Okay, then here we have a metallic conductor. This is a battery. You have to be already familiar with the symbols of the electrical components. This is ammeter, this is a voltmeter. You know, ammeter is connected in series with the component, voltmeter is connected across the component. So there is current flowing. Now, you know, greater the current, this is fixed, R is fixed. So greater the current, greater the potential difference V. Okay, we'll see that using the equation. We will learn about Ohm's law, and then when you learn about Ohm's law, you will learn this equation V equals IR. Now what happens is, when the potential difference across this increases, and if the resistance is the same, the current increases. So that's what you can see over here. Okay, when this is constant, and if one quantity increases, the other also increases it in a direct proportion relationship. Okay, to help you all understand better, I have drawn this diagram. We have this equation. Now I already explained this. Now in addition to this, you can see that if I have a graph of v versus I, okay, you have here on the y-axis v, on the x-axis I. So this has been rearranged in the form y equals mx plus c, but the plus c part is 0 because there is no y-intercept. That means it passes through the origin. So this is a straight line passing through the origin. Now you can see on the y-axis we have v, on the x-axis we have I. The gradient is r. The gradient is r. Okay, so if you have a graph of v versus I, the gradient will be r, and it will be a straight line passing through the origin, which means v is directly proportional to I. Similarly, we can have I on the y-axis and v on the x-axis. Now we will again rearrange this equation so that we get it in this form. Okay, move the r to the other side, then it becomes v over r equals I. Okay, so here we have v over r equals I. Then again rearrange like this. So you have on the y-axis you have I, on the x-axis you have v, and the gradient is now 1 over r. So if you plot a graph of I versus v, the gradient is 1 over r. Okay, remember, if it's v versus I, the gradient is r. I'm mentioning this because sometimes students confuse this. Alright, then back to the book. Here we have Ohm's law. You have to know this definition. In this book, whatever is in the green boxes is extremely important. You have to memorize it with understanding because these are the definitions. Now in the exam papers they can ask you to write what is Ohm's law, state Ohm's law. Then this is what you need to write. And also in your glossary, the meanings of these words that are in green bold letters are at the back of the book in the glossary. So you have to know the meanings of those words. Whatever in your book is that is in green bold letters, for example this, okay, those words are important. You have to memorize the meanings of or the definitions of them with understanding, because in the exam papers, especially in paper 2, they ask you to state it. Paper 2, and if you are doing A2, paper 4 also, they ask you to write the definitions. Okay, Ohm's law. A conductor obeys Ohm's law if the current is in it is directly proportional to the potential difference across its ends. So that is this equation. Okay, so you have to be able to write this, and you should also know the equation. And this thing also I already explained. Resistance is 1 over gradient if it's a I versus V graph. Now this is for a material with a constant resistance, but usually what happens is when the temperature increases, the resistance increases. So when the resistance increases, this graph will curve downwards. Okay, because the resistance increases means the gradient should decrease. Now the gradient of I versus V graph I showed you earlier is 1 over the resistance. Sorry, the resistance is 1 over the gradient. Okay, so over here the previously, I'll show you again. Previously we saw that the gradient is r, gradient here is 1 over r. So with increasing temperature, with time, what happens is the temperature increases. When the temperature increases, the resistance increases, and therefore the gradient decreases. So this will curve this way. In other words, this graph will curve this way. The gradient of this graph will decrease when the resistance increases. Okay, but if it was a V versus I graph, when it will curve in the other direction, because when the resistance increases, this gradient is resistance, it will curve in that upward direction. Okay, then this is what I talked about earlier. Now we can go into the details of how the resistance of a material increases with increasing temperature or decreases with decreasing temperature. Okay, so this is what I explained earlier. If it's a I versus V graph, the gradient is 1 over the resistance. So when the resistance increases, the gradient decreases. So it curves this way. Now here this is for the negative values. If you connect it the other way around, now when we did the practicals in our lab, you notice that if you connect the multimeter the other way around, it will give negative reading. So if you switch the terminals, it will give a negative reading for the current and a negative reading for the voltage. So that is for this negative part that they are showing. Alright, there are some points you should notice about the graph. The line passes through the origin as for an ohmic component. Now if it's an ohmic component, you should get this kind of graph. It should be a straight line passing through the origin. If a component is an ohmic component, it obeys Ohm's law. If it's a non-ohmic component, it doesn't obey Ohm's law. This will not be a straight line. So you have to remember this also. What is an ohmic component and what is a non-ohmic component? If it's an ohmic component, it obeys Ohm's law. The graph of I versus V or V versus I will be a straight line passing through the origin. The line passes through the origin as for an ohmic component. Now you can see that over here in the initial part, this is the graph for a filament lamp, IV characteristic for a filament lamp. So in the beginning it is a straight line, but afterwards it curves. Alright, for very small currents and voltages, the graph is roughly a straight line. See over here, it's roughly a straight line. At higher voltages, the line starts to curve. You know, higher the voltage, the more it curves like this. The current is a bit less than we would have expected from a straight line. When it curves this way, you can see the current is less than what is expected, because if it was a straight line for that same voltage, the current will be higher, but it curves this way, so for the same voltage the current is lesser than expected. This suggests that the lamp's resistance has increased. I told you how depending on the shape of the graph the resistance is. You can also tell that the resistance has increased because the ratio V versus I is larger for higher voltages than for low voltages. In fact, the graph of 11.4 is not a straight line through a straight line. It's not a straight line, shows that the resistance of the lamp depends on the temperature of its filament. Its resistance may increase by a factor as large as 10 between when it is cold and when it is brightest, when its temperature may be as high as 1750 degrees Celsius. So higher the temperature, greater will be the resistance for a material. And especially metals, we will learn in detail under the structure of the metal, the metallic bond and all of that. Okay, previously I mentioned about thermistors. So this is what the same thing that I explained previously at the beginning of this chapter. Thermistors, also called thermal resistors, are made from metal oxides such as those of manganese and nickel. Remember the materials. There are two distinct types of thermistors. I already explained. Yeah, so this is you can go through it. Then PTC also I explained. The resistance of this type of thermistor rises abruptly at a definite temperature, usually around 100 to 150 degrees Celsius. Okay, then the change in their resistance with temperature gives thermistors many uses. Here are some uses of thermistors. Water temperature sensors in cars and ice sensors on aircraft wings. If ice builds up on the wings, the thermistor senses this temperature drop and a small heater is activated to melt the ice. You know, in aeroplane wings, this can be used so that it triggers the heater. Baby alarms. The baby rests on an air-filled pad, and as he or she breathes, air from the pad passes over a thermistor, keeping it cool. If the baby stops breathing, the air movement stops, the thermistor warms up and an alarm sounds. Then we have it in fire sensors. A rise in temperature activates an alarm. Overload protection in electric racer sockets. If the racer overheats, the thermistor resistance rises rapidly and cuts off the circuit. Okay, so here is the filament lamp. This is the graph for that. And in the previous page also we'll just go through it so that we are sure that we have covered everything. Okay, so you can see the IV characteristic for a filament lamp. Okay, it's actually this graph. Okay, so you have to do all these questions in the brown boxes. It's very important. Then here we have another non-ohmic electrical component. Why it's non-ohmic? Because it's not the graph of this I versus V or V versus I is not a straight line passing through the origin. If it was a straight line passing through the origin, then the component is an ohmic conductor. For example, we saw it for the conducting material, the metallic conductor. For example, a wire, it's a straight line. So this is an ohmic conductor. Alright, let's move on. And the diodes are also very important. You have to know how these things work. It lets current flow in one direction but doesn't let the current flow in the opposite direction. In the O-level class also you have learned this. A diode is any component that allows electric current in only one direction. Nowadays most diodes are made of semiconductor materials. One type, the light emitting diode or LED, gives out light when it conducts. You have seen LEDs in our homes also we use, but if you the LEDs, it lets current flow only in one direction, and when the current flows it gives out light. If you connect the LED the other way around, it doesn't let current flow, so it doesn't emit light when it's connected the other way around. Okay, so we call this forward bias and reverse bias. When you connect it the correct way around, it conducts, and we call it forward bias. If you connect it the other way around, it doesn't conduct, we call it reverse bias. There are some points you should notice about the graph. Now over here you can see after it passes a certain voltage only it will start conducting, but before that it doesn't conduct even if it's connected the correct way around. We have included positive and negative values of current and voltage. This is because when connected one way round, positively biased. Okay, so this is what I explained earlier, positively biased, B-I-A-S-E-D, not bias, biased. The diode conducts and has a fairly low resistance. Connected the other way around, negatively biased, it allows only a tiny current and has almost infinite resistance. For positive voltages less than about 0.6, the current is almost zero, and hence the diode has almost infinite resistance. See, up to here. It starts to conduct suddenly at its threshold voltage. So what's the threshold voltage? 0.6 volts. You have to know the meanings of these words. Okay, so it comes to a certain limit, maximum. That's what we call a threshold. Okay, so in this case it's a threshold voltage. The resistance of the diode decreases dramatically for voltages greater than 0.6 volts. Okay, so you can see the resistance of a diode depends on the potential difference across it. From this we can conclude that it does not obey Ohm's law. It is a non-ohmic component. Okay, in the A2 class you will learn about diodes being used as rectifiers, and you would have also learnt in the O-level class what a rectifier is. Okay, the current against potential difference IV characteristic. So you see IV graph or IV characteristic for a diode. The graph is not a straight line. A diode does not obey Ohm's law, so it's a non-ohmic conductor. Okay, then diodes are used as rectifiers. They allow current to pass in one direction only, and so can be used to convert alternating current into direct current. So that rectifier converts alternating current to direct current. So that's what a rectifier does. There is more about this in chapter 29, so you can refer chapter 29. That's why I told you in the A2 class you will learn more about rectifiers. Most modern diodes are made from silicon and will start conducting when there is a potential difference of about 0.6 volts. So this is what we call the threshold voltage. You need to remember this key 0.6 volt value. I told you it's important that you know the meaning, and you have to remember this 0.6 volt is the threshold voltage. When the voltage is more than this, and if it's positive, if the diode is positively biased, that means connected the correct way around, then it will conduct. Okay, so you also have to know how the resistance is affected by the purity of the metal. Okay, so that's what we have here. Okay, first we'll go through this part. It's only a little bit. LEDs have traditionally been used as indicator lamps to show when an appliance is switched on. Newer versions, some of which produce white light, are replacing filament lamps, for example in traffic lights and torches, flashlights. See figure 11.8. So here this has LEDs. This torch has 7 white LEDs giving a brighter whiter light than a traditional filament lamp. Nowadays in our houses also we use LEDs instead of the traditional light bulbs. Although they are more expensive to manufacture, they are more energy efficient and hence cheaper to run, so that the overall cost is less. Okay, now you learned about the threshold voltage for diodes. The threshold voltage at which an LED starts to conduct and emit light is higher than 0.6 volts and depends on the color of light it emits, but may be taken to be about 2 volts. So for LED it's about 2 volts. Okay, now the next part is about purity of the metal and how well it conducts. Okay, or in other words we can say how much its resistance will be. Now you can see if it is impure, the resistance is higher. If it's pure, the resistance is lower. See, with increasing temperature you know that the resistance increases. Now we will learn about it afterwards, how this resistance increases in a metal with increasing temperature. It has to do with the vibration of the particles also. Okay, understanding the origin of resistance. To understand a little more about the origins of resistance, it is helpful to look at how resistance of a pure metal wire changes as its temperature is increased. This is shown in the graph of figure 11.9. You will see that the resistance of the pure metal increases linearly as the temperature increases from 0 to 100 degrees Celsius. It's increasing linearly, straight line. That's what we mean by linear. Compare this with the graph of figure 11.10 for an NTC thermistor. The thermistor's resistance decreases very dramatically over narrow over a narrow temperature range. Okay, so 11.10, this is for the thermistor. You can see it's actually a question. When the temperature increases, the resistance decreases. I told you what NTC thermistor is. NTT, negative temperature coefficient thermistor. So in these thermistors, the temperature decreases when the resistance decreases when the temperature increases. Okay, so narrow temperature range from 0 to 100 here, from 0 to 70 decreases dramatically, huge decrease over a small temperature range. The resistance of a metal increases gradually as its temperature is increased. The resistance of an impure metal wire is greater than that of a pure metal wire of the same dimensions. See, same dimensions, you remember this. Okay, now we will learn how the temperature increase causes an increase in resistance of a metal, especially a metal. Okay, even in the other materials that conduct, the resistance increases with increasing temperature, because the vibration of the particles increase. So you know, temperature is a measure of the average kinetic energy of the particles in a substance. So if the higher the temperature, higher the average kinetic energy. Okay, so in other words, they vibrate faster. Now when they vibrate faster, what happens is the delocalized electrons, also called the conducting electrons, have difficulty passing through. You see here, now if there was no vibration, now this is what happens in a superconductor. In a superconductor what happens is, if you cool a metal below something called the critical temperature, the vibration of these metal ions stop. When it stops, the electron can directly move through. So the resistance is almost zero. That is what we call a superconductor. Okay, but normally all the metals normally that is at room temperature are above its critical temperature, so they are not superconductors. So even when you have not heated a metal, still there are vibrations. So this causes the electron to not move as fast as it can move when it is a superconductor. And if you heat more, what happens is the vibration of these metal ions will be more, and then these electrons have even more difficulty passing through. It is these electrons that conduct. You know, the reason metals are good conductors is because they have free electrons or mobile electrons in the sea of electrons. Okay, so if you remember the metallic bond that you learned in the O-level class, you would have learned even in the A-level class, you would have learned about sodium, magnesium, aluminium. So if you go along that period where you have In the first group sodium, second group magnesium, third group aluminium. In the sodium there is 1 electron in the outer shell. In the magnesium you have 2 electrons in the outer shell. In aluminium you have 3 electrons in the outermost shell. So these electrons are the electrons that are given to the sea of electrons, and that those electrons conduct. So aluminium, since it gives 3 electrons to the sea of delocalized electrons, and magnesium gives 2, and if you see sodium gives only 1, the best conductor out of those 3 is aluminium, then magnesium, and the least conducting is sodium, okay, out of those 3. Okay, so it depends on how many electrons each atom gives to the sea of electrons. Now when the metal atom gives the electron to the sea of electrons, it becomes a metal ion. So that's why they have drawn these as ions. Okay, figure 11.10 also shows how the resistance of the metal changes if it is slightly impure. Now you can see this is when it is impure. So impure means it has atoms of other elements in it. So like you see here, see these bigger bigger spheres are the atoms of the other elements. So this is an impure metal. Now what happens is it hinders the movement of electrons even more. So that's why when a metal is impure, the resistance is higher. Okay. The resistance of an impure metal is greater than that of a pure metal and follows the same gradual upward slope. The resistance of a metal changes in this gradual way over a wide range of temperatures, from close to absolute zero up to its melting point, which may be over 2000 degrees Celsius. So some metals have melting points of over 200 degrees Celsius. You know, tungsten has a very high melting point. That's why we use tungsten in the filament lamps. That filament of a filament lamp is made of tungsten. Okay, so what we can say is this suggests that there are 2 factors which affect the resistance of a metal. One is temperature, the other is presence of impurities. Higher the temperature, higher the resistance. Greater the impurities, or we can say the impure a metal is, the higher the resistance compared to a pure metal. Figure 1.11 shows a simple model which explains what happens in a metal when the electrons flow through it. Okay, so I already explained this, and you would have learned about drift velocity. Okay, you would have learned the equation I equals NAVQ, and V is the drift velocity, okay, which is an average velocity. Now they are actually explaining about the drift velocity also. Okay, so you can see over here diagram A and B. At low temperatures, electrons flow relatively freely. At higher temperatures, the electrons are obstructed by the vibrating ions and make very frequent collisions with the ion. So it collides with this, it has difficulty passing through. Impurity atoms can also obstruct the free flow of electrons. Okay, in a metal, a current is due to the movement of free electrons. At low temperatures, they can move easily past the positive ions. That is in figure 11.11a, the first one. However, as the temperature is raised, the ions vibrate with larger amplitudes. So these ions vibrate with large amplitudes the greater the temperature. The electrons collide more frequently with the vibrating ions. Okay, so when it is vibrating, there will be more frequent collisions with the electrons, so then their speed is reduced, and this decreases their mean drift velocity. So see, mean means average, okay, drift velocity. So remember this in the equation I equals NAVQ, V is an average drift velocity. Okay, so average is not the velocity of one, it's the velocity of all of them. You get the average. Okay, the electrons collide more frequently with the vibrating ions, and this decreases their mean drift velocity. Why I emphasized on this was because there was a question where they asked whether it's a mean drift velocity. Okay, they lose energy to the vibrating ions, figure 11.11b. Okay, if the metal contains impurities, some of the atoms will be of different sizes. Again, this disrupts the free flow of electrons. In colliding with impurity atoms, the electrons lose energy to the vibrating atoms. Okay, okay, so what happens is, now when these electrons collide with the metal atoms, they make them vibrate even faster because energy is transferred from the electron to the metal atom. So when they vibrate even faster, temperature is a measure of the average kinetic energy of the particles in a substance. So they vibrate even faster. So faster vibration means greater kinetic energy. So greater kinetic energy means higher temperature. So they give up the energy. So this is about the electrons when they collide with the vibrating ions or impurity, they give up energy to the metal, so it gets hotter. The resistance of the metal increases with the temperature of the wire because of the decrease in mean drift velocity of the electrons. So the speed with which the electrons flow is reduced. So that's why we say the resistance of the metal increases. Current is charge over time. So if you have less charges flowing in a certain time period, that means the current is reduced. Conduction in semiconductors is different. Now in semiconductors, what happens is, when you increase the temperature, it gives out more free electrons. The atoms give out more free electrons or delocalized electrons. So that increases the that decreases the resistance. So in semiconductors, when you increase the temperature, more free electrons are released, so the resistance decreases. So that is what we use in NTC, negative temperature coefficient thermistors. At low temperatures, there are few delocalized or free electrons. For conduction to occur, electrons must have sufficient energy to free themselves from the atom they are bound to. As the temperature increases, a few electrons gain enough energy to break free of their atoms to become conduction electrons. The number of conduction electrons thus increases, and so the material becomes a better conductor. At the same time, there are more electron-ion collisions. But this effect is small compared with the increase in the number of conduction electrons. So what this means is, in a semiconductor, compared to the number of collisions that are occurring to slow down the movement of electrons, more free electrons are released when the temperature is increased. Okay, that's what this last sentence means. So overall, what happens is, in a semiconductor, when the temperature is increased, the resistance decreases because more free electrons are released. So current is charge over time. So in a certain period of time, even though the speed of the electrons is decreased, more electrons are released. So more charge particle or charges or electrons flow in a certain unit time. I equals Q over T. So you can imagine that equation, I equals Q over T. So if you have more Qs, more charges in a certain time period, the current increases. Okay, then finally we have this equation, R equals rho L over A. This is a very important equation. They would have given a diagram. Okay, no, they haven't given a diagram. Then maybe we need to draw it. Okay, so resistivity, I told you, depends on the material. So different materials, you can see here, have different resistivities. Okay, so this is the important equation that you need to know how to use. Let's see what happens. Okay, so what happens here is, now for a material, rho is constant. Okay, so if you have wires of the same cross-sectional area, same material, but longer length means greater resistance. So if rho and A are constant, greater the length, greater the resistance. Okay, so that also I think they have shown. Yeah, see, greater the length, greater the resistance. So resistance is directly proportional to the length, and greater the cross-sectional area, lesser the resistance. Okay, so again, if you look at this equation, if rho and L are constant, now imagine you have wires of the same material, because rho depends on the material. Okay, the rho is the resistivity depends on the material. So if you have two wires of the same material, same length, but if one wire has a larger cross-sectional area, then it will have a lower resistance. Alright, I have drawn a diagram to help you understand this better. L is the length of the conductor. So this green thing you see here is the length of it's a wire. Okay, so it can be any wire. It can even be it doesn't even need to be a metal. You can see here they have given for other materials also, this silicon, pyrex glass, graphite, germanium. Alright, so let's say we have one of those materials here, rho, that is the resistivity of the material. Now you can see this A here is the area of cross section. If you cut it like that, this is the area of cross section, and L is the length of that conductor or material. Okay, so you can see here, if you have a longer length, the resistance will increase provided these two quantities are kept constant. And if you have a larger cross sectional area for the same length, same resistivity, then the resistance will decrease. Why? Because if you have a larger cross sectional area, there is more space for the electrons to move, so they can move easily. That reduces the resistance. Okay, so you have to be able to use this equation. Now you don't need to memorize these values. These values of resistivity will be given to you, and you have to know the unit. Okay, ohm meter, you can figure it out from the equation also. Now you see over here, if you move this to this side, if you make rho the subject of the equation, as you can see, I have done it here. Rho is equal to Ra over L. The unit of this will be ohm, the unit of this will be meter squared in SI units, the unit of this will be meters. So when you simplify, the unit of resistivity will be ohm meters. Ohm meters. Okay. Yeah, here is an example. Find the resistance of a 2.6 meter length of Eureka wire with cross-sectional area 2.5 into 10 to the power of minus 7 meter squared. So R equals rho L over A. We are using this equation. Very simple. Substitute the values. Length is 2.6 meters. Cross-sectional area is also given, 2.5 into 10 to the power minus 7 meter squared. And what about the resistivity? Now I told you, you don't need to memorize it. It will be given to you. It's in table 11.2. This is Eureka wire. Okay, this is also in SI units, 49 into 10 to the power minus 8. Substitute, use your calculator, and you will get 5.1 ohms. Okay, then resistivity and temperature. Resistivity, earlier we saw resistance and temperature. Now we are seeing resistivity and temperature. Resistivity, like resistance, depends on temperature. For a metal, resistivity increases with temperature. So this is what you need to know. Just like resistance, resistivity also increases with temperature. As we saw above, this is because there are more frequent collisions between the conduction electrons and the vibrating ions of the metal. Okay, that is the end of that chapter. You have to answer all these questions. All right, very, very important, because you have to do this, because these are the basic questions. So once you answer the questions in the brown boxes, you will come to a position where you are able to you have the knowledge to answer the past paper questions. Okay, so this is the minimum that is required for you to answer the past paper questions. So make sure you do in every chapter all the questions in the brown boxes, and check your answers. If you have any difficulty, you have to ask me. Now one more thing is, we will go through this chapter and check whether we missed anything. Okay, by the way, you can see there are other ways that you have to check what happens in this equation. For example, now this is a wire. Okay, the surface area is area of a circle. So over here you can see this area, surface area is the area of a circle, and we know the area of a circle is given by pi r square. Most of the questions that you get don't have the area given directly to you. They will usually give you the diameter of the wire. Okay, so when you have the diameter, you know the formula for cross-sectional area, that is pi r squared. Okay, so A is equal to pi r squared. This is the area of a circle. So if you want to find this area, you have to use this. But also, you know, a radius of this, okay, of a circle, radius of a circle is diameter divided by 2. Diameter divided by 2. So over here we can substitute for r, diameter divided by 2 quantity squared. Okay, So here you can see, then you will get pi d squared over 4. And finally we can conclude that the area of cross section is proportional to the square of the diameter. Okay, so this is what you have to understand. And if you increase the length, what happens? So let's say you add another one in series with this. It's the same as like having a longer length. And what happens is the total resistance increases. So if you add everything like this identical one in series with this, it's as if you have a longer length of this. So when that happens, what? You know the equation that we use for combined resistance, R equals R total. The equivalent resistance is equal to R1 plus R2 like this. So if you have another one, then the resistance increases. If it's identical same length, if you double the length, the resistance will double. Okay, but over here when it comes to the area of cross section, when you double the diameter, the area of cross section will quadruple. It will be 4 times that. Okay, so again, if you have a wire with double the diameter of, let's say, the original wire, if you are comparing the resistance with the original resistance, so if you double the diameter, if you have a wire with double the diameter, the area of cross section of that wire will be 4 times of that. Okay, so 4 times. In other words, we can say the resistance will become quarter. The resistance of the new wire will be quarter the resistance of the original wire, if the diameter is double, or in other words, if the area of cross section is quadrupled. So when the diameter is double, the area of cross section quadruples and the resistance decreases by a factor of 4. Okay, when you do questions, you will understand this. Okay, so here they explain in terms of like it's like connecting the resistors in parallel. Okay, if you have let's say another one like this connected like this, so that will make the length is the same, but what happens is the area of cross section doubles. So when the area of cross section doubles, the resistance halves. It's like connecting 2 resistors in parallel. Okay, doubling the area of cross section is like connecting another one like this next to it. Okay, connecting it in parallel. But if you connect it next to it like this, then you are connecting in series. You are doubling the length. If you connect an identical one like this in series, you are doubling the length. That will double the resistance. If you connect an identical one like this parallel to this, then you are doubling the area of cross section. That will halve the resistance, because 2A, then this will be half. Okay, so that's what is meant by these 2 points here. Then we'll have a look at this also. You have generally you should know what is nichrome. It's an alloy of nickel, copper and aluminium, and also used in electrical heaters because it does not oxidize at 1000 degrees Celsius. Then previously you would have learned this: nichrome, manganese, tungsten, tungsten, those are all materials of high resistance used in resistance wire. Manganese, an alloy is a mixture of metals. Okay, now even steel is an alloy, but there you have iron and carbon. Manganese, an alloy of 84% copper, 12% manganese and 4% nickel. Eureka, also called tungsten, an alloy 60% copper and 40% nickel. Now here you have another alloy. Sorry, this is nickel, right? Not nichrome. Okay, don't confuse the two. Okay, so polytetrafluoroethane or Teflon. For chemistry, you all would have learned this. Okay, so here are the values. We went through this part. Okay, we went through all of this. I don't think we missed anything here. LEDs we went through. This also we discussed in detail. About thermistors also we discussed in detail. Resistance and temperature, Ohm's law. Then gradient of the graph also we learned. Then we come to the very first page of this. Okay, we went through the whole chapter, and it seems like we have covered everything. For the last part, we will go through the summary. A conductor obeys Ohm's law if the current in it is directly proportional to the potential difference across its ends. I already explained this. I wrote the equation, I drew the graphs, and I told you what directly proportional is. It has to be a straight line passing through the origin. If it's just a straight line, we say it's a linear relationship. Okay, for it to be a proportion, two conditions. It has to be a straight line, it has to also pass through the origin. Then ohmic components are components which obey Ohm's law. So if you draw a graph of V versus I or I versus V, it will be a straight line passing through the origin. Ohmic conductors include a wire at constant temperature and a resistor. So remember these two ohmic conductors, wire and resistor. Non-ohmic components include a filament lamp and a light emitting diode. Why? Because the IV characteristic or IV graph of these components are not straight lines, they curve. So for it to be an ohmic conductor, it has to be a straight line, because Ohm's law states that Ohm's law states, okay, again you have to memorize the Ohm's law. A conductor obeys Ohm's law if the current in it is directly proportional to the potential difference across its ends. Okay, so if it's a straight line only passing through the origin, it will obey Ohm's law. Otherwise, it's a non-ohmic component. Filament lamp and a light emitting diode. Okay, so you remember some examples like this. A semiconductor. Okay, another example would be the NTC thermistor, negative temperature coefficient thermistor. Okay, so that's also a non-ohmic conductor. We saw the graph previously in a question. See, this is the graph. So as long as it's not a straight line, it's a non-ohmic conductor. IV graph is not a straight line. Okay, a semiconductor diode allows current in one direction only. As the temperature of a metal increases, so does its resistance. A thermistor is a component which shows a rapid change in resistance over a narrow temperature range. So rapid change in resistance over a narrow temperature range. And we saw the graph also, how the resistance varies with temperature. Again, if you want, we can have a quick look at it. See, from about 6.5 ohms, it drops to about 1 ohm in a range of temperature range of about 80 degrees Celsius. The resistance of an NTC thermistor decreases as its temperature is increased. The resistivity ρ of a material is defined as ρ equals RA over L. I showed that over here to you using this equation. We made ρ the subject of the equation. Resistivity is ρ, where R is the resistance of a wire of that material. Okay, so again I drew everything and I showed you all of this. I'll just move it to this side so you can have a better look when we are going through this. Oops. Okay, so that's better. Yeah, where R is the resistance of a wire of that material, A is its cross-sectional area, so you can see that's all labeled, and L is its length. Some textbooks use simple L, some textbooks use capital L for the length. This textbook here uses capital L in this chapter. The unit of resistivity is the ohm meter. Okay, so that concludes that chapter on resistance and resistivity. Again, make sure you do all the questions in these brown boxes. Check your answers with the solutions to the book, and after that you can start doing the end of chapter questions, or you can start doing the questions in those past paper books. Okay, there are a lot of past paper questions arranged by topic. You have to do those questions in the drive also, and you have to also do the questions in the past paper book which has the solutions. Okay, all right, that's the end of the chapter.